Hello everyone, welcome to my presentation. Let me start by saying few words about my own. So my name is Garima MORE, a second year engineering student at DAVV-IIPS. As you can see on the screen, I have created a playlist on video solutions of NAD internal papers under guidance of Mr. Shaligram Prajapat sir. The content of this presentation are internal first, internal second part A as internal test 2, internal second part B as internal test 3. So in this video we're gonna discuss the topic of internal 1 are as follow: error, transcendental and algebraic equations, degree of a polynomial, floating point representation, their operation and algorithms, and arithmetic and distributive law for arithmetic digits. So let's move to the question first. Write an algorithm to accomplish the task for polynomial p of x given in the following table. P of x is equal to an xn plus an minus 1 xn minus 1 and so on. तो as you can see हमें यहाँ पे टेबल दी गई है जिसमें टास्क है. इन टास्क पर हमें इटरेटिव अप्रोच और रिकर्सिव अप्रोच की एल्गोरिथम बतानी है. So हम एल्गोरिथम बता रहे हैं. Algorithm for evaluating the polynomial p of x using brute force technique. Iterative approach. First, initialize the sum variable as to 0 for each term of the polynomial from highest to lowest degree. Compute the value of the term by multiplying the coefficient with x raised to the degree of the term. Second, add the computed value to the sum variable as. Return the value of s as the value of polynomial p of x. Algorithm for evaluating the polynomial p of x using recurrence relation recursive approach. If the degree of the polynomial is 0, return the value of the constant term a0. Otherwise, compute the value of p of x recursively by a. Computing the value of the polynomial of degree n minus 1 by calling the function with the polynomial of degree n minus 1 as argument. B. Computing the value of the current term by multiplying the coefficient with the x raised to the degree of the term. C. Adding the computed value to the polynomial of degree n minus 1. Return the value of the polynomial p of x. Algorithm for dividing polynomial p of x by x minus r. Initialize the quotient polynomial q, reminder r to 0 for each term of the polynomial from highest to lowest degree. Compute the value of the current term of the quotient by dividing the coefficient by x minus r. Add the computed value to the quotient polynomial q. Compute the value of the current term of the remainder by multiplying the quotient of the current term with x minus r. Subtract the computed value from the current term of the polynomial. Add the computed value to the remainder polynomial r. Return the quotient q and remainder r. Algorithm for computing the derivative of polynomial p of x is: first, initialize the derivative polynomial d to 0. Second, for each term of the polynomial from highest to lowest degree, a. Compute the value of derivative of the current term by multiplying the coefficient with the degree of the term and subtracting 1 from the degree. B. Add the computed value to the derivative polynomial d. Third, return the derivative polynomial d. Question 2. Write the algorithm flowchart of the following task and complete the table. As you can see on the screen, हमें यहाँ पे task data 1 and data 2 given है और हमें error और final result हमें यहाँ पे fill करना है. First operation is subtraction. The operation of subtraction is nothing but adding a negative number. The subtraction of 0.5452 with exponent e minus 99 and 0.5424 with exponent minus 99 leads to the answer 0.0028 exponent with minus 99. Again, the mantissa is shifted left for normalization. In this process, the exponent is reduced by 1. The exponent would thus become minus 0 with the first left shift. As the exponent in our hypothetical computer can store only two digits, 100 cannot be accommodated in the exponent part of the number. So 100 cannot be accommodated in the exponent part of the number. In this case, the result is smaller than the smallest number which could be stored in this hypothetical computer. This condition is called an underflow condition, and arithmetic unit will signal an error condition. Now subtraction on data 2. Subtract 5424 with exponent e3 from 0.5452 with exponent e3. The exponents are equal, thus the mantisas are subtracted. The result is 0.0028 e3 as the most significant digit of the mantissa is 0. The mantissa is shifted left till the most significant digit is non-zero. For each left shift of the mantissa, the exponent is reduced by 1, thus the result is 0.2800 E1. Now multiplication. Two numbers are multiplied in the normalized floating point mode by multiplying the mantissas and adding the exponents. After the multiplication of mantissas, the result mantissa is normalized as in addition operation oblique subtraction operation and the exponent appropriately adjust. यहाँ पे हमें डाटा वन एन वन और एन टू दिया गया है। एन वन से एन टू को मल्टीप्लाई करने पर हमें उसका आंसर मिलता है 0.04937284 विथ एक्सपोनेंट E101। एक्सपोनेंट को ऐड किया गया है तो एक्सपोनेंट हमें 101 मिला है। ये कंडीशन ओवरफ्लो थ्रो करती है तो फाइनल आंसर इसका होगा 0.4937 E100। यहाँ पे हमें एक्सपोनेंट 100 लिया है क्योंकि हमने वेंटिसा को राइट शिफ्ट किया है। नाउ मल्टीप्लिकेशन ऑन डेटा टू। N1 और N2 को हम मल्टीप्लाई करेंगे तो हमें आंसर मिलेगा 0.0137097 और एक्सपोनेंट को ऐड करने पर हमें मिलेगा एक्सपोनेंट 25। यहाँ पे हम 0974 डिस्कार्ड कर देंगे तो हमारा फाइनल आंसर है 0.1370 E24। Now division. In dividing a number by another, the mantissa of the numerator is divided by that of the denominator. The denominator exponent, the quotient mantissa is normalized to make the most significant digit non-zero, and the exponent appropriately adjust. The mantissa of the result is chopped down to occupy 4 digits. डिवीजन ऑपरेशन डेटा वन पे परफॉर्म कराया। यहाँ पे n1 इज इक्वल टू 0.998 विद एक्सपोनेंट e1 एंड n2 इज इक्वल टू 0.1000 e -99। इस पर जब हमने डिवीजन ऑपरेशन परफॉर्म कराया तब हमारा आंसर आया है 9.9980 एक्सपोनेंट 100। इस पे हमने मेंटिसा को राइट शिफ्ट किया तब हमारा रिजल्ट है 0.9998 विद एक्सपोनेंट 101। यह ओवरफ्लो कंडीशन थ्रो करता है। सिमिलरली हमने डेटा टू पर डिवीजन ऑपरेशन परफॉर्म किया। n1 is equal to 0.9998 with exponent e-5 and n2 is equal to 0.1000 with exponent e98। इन पर हम डिवीजन ऑपरेशन परफॉर्म कराया तब हमारा फाइनल रिजल्ट आया 0.9998 with exponent e-104। ये कंडीशन अंडरफ्लो है। Flowchart for subtraction. Start. Read n1 n2. Here the condition is e1 is equal to e2. If condition is true, then yes, resultant m will be answer of m1 minus m2 and exponent will e1 or e2. If number is normalized, yes, then print mantissa and exponent and stop. If number is not normalized, then normalize m1 by shifting decimal point for the range 0 and 1 and 0.n2 with decimal points so on for each shift of mantissa adjust exponent. Here another condition, e is greater than 99, condition is yes, print overflow error, and if exponent is smaller than -99, then condition is yes, print underflow error. We will go to the E1 and E2 condition. If E1 is greater than E2, if yes, then shift M2 by E1 and E2 um, with subtraction operation, and resultant mantissa will be M1 minus M2 and exponent will be E1. If condition is no, then shift M by E1 minus E2 and the resultant mantissa will be M1 minus M2 and exponent will be E2. Flowchart of multiplication. Start. Read n1 and n2. M will be the result of m1 multiplication between m1 and m2 and exponent will be e1 plus e2. The condition is if m is normalized, if yes, print mantissa and exponent and stop. If m is not normalized, then normalize m by shifting decimal points for the range 0 and 1 and 0.2 decimal points for each shift of mantissa adjust exponent. If E is greater than 99, print overflow error, and if E is less than minus 99, then print underflow error. Flowchart for division start again, read n, n1 and n2. M will be the result of m1 divided by m2 and exponent will be e1 minus e2. The condition is if m is normalized, if yes, print mantissa and exponent and stop. If condition is not normalized, means m is not normalized, normalize m by shifting decimal points for range 0, 1 and 0.2 with decimal points for each shift of mantissa, adjust exponent. Here another condition, if E is greater than 99, if yes, print overflow error, and no, then E will be smaller than minus 99. Condition is print underflow error. Let's move on the question 3. Verify associative law and distributive law of arithmetic with fitting for mantissa digits and provide correct answer if no number is truncated. Case 1. A plus B minus C is not equal to A minus C plus B. Um, A is equal to 0.5665 with exponent E1, B is equal to 0.5556 with exponent E minus 1, and C is equal to 0.5644 exponent 1. And case 2 is A bracket in bracket B minus C is not equal to AB minus AC, and A is equal to 0.5555 with exponent E1, B is equal to 0.5454, sorry 4545 with exponent e minus 1, and c is equal to 0.4535 with exponent e1. Case 1. To verify the associative law and distributive law of arithmetic with fitting for mantissa, we need to perform the operation on the given values and check if the result satisfy the law. Let a is equal to 0.5665 exponent e1, b is equal to 0.556 e minus 1, C is equal to 0.5644 E1. A प्लस बी हमने कराया तो हमारा रिजल्ट आया 0.570 एक्सपोनेंट E1. A प्लस बी माइनस सी करेंगे तो 0.5720 E1 माइनस 0.5644 E1, यहाँ पे 0.5720 E1 रिजल्ट है हमारा एडिशन ए और बी का. सो आंसर आएगा 0.7600 E माइनस 1. ए माइनस सी करेंगे तो हमारा आंसर आया 0.2100 E माइनस 1. ए माइनस सी प्लस बी करने पर हमें आंसर मिला 0.7656 E1. So हमें पता चला it is thus we seen that a plus b minus c is not equal to a minus c plus b. In other words, the distributive law and the associative law does not hold for these values. In fact, the correct answer if no number is truncated is 0.7656 e minus 1. It is thus seen that floating point representation is that the associative and the distributive laws of arithmetic are not always valid. Case 2. To verify the associative law and distributive law of arithmetic with fitting for mantissa digits, we need to perform the operation on the given values and check if the result satisfy the law. So let a is equal to 0.5555 exponent 1, b is equal to 0.4545 exponent 1, and c is equal to 0.54535 e1. b minus c ऑपरेशन परफॉर्म करने पर 0.0010 e1 रिजल्ट आया 0.100 e माइनस 1. यहाँ पे हमने मेंटिसा को राइट शिफ्ट किया है. हमारे जो रिजल्ट है उसमें हम ए मल्टीप्लाई करेंगे तो हमारा रिजल्ट आएगा 0.0555 E0. मेंटिसा को 1 डिजिट राइट शिफ्ट करने पर हमें एक्सपोनेंट E माइनस 1 मिला. नाउ A इंटू बी 0.5555 एक्सपोनेंट E1 इंटू 0.4545 E1 हमें रिजल्ट मिला 0.2524 E2. ए इंटू सी करने पर हमें रिजल्ट मिला 0.2519 E2 एंड ए बी माइनस ए सी इज इक्वल टू 0.500 E-1. Thus, A of B minus C is not equal to AB minus AC. It is thus seen that floating point representation is that associative and distributive law of arithmetic are not always valid. In other words, A of B plus C is not equal to AB plus AC, and also for A of B minus C is not equal to AB minus AC. It does not valid for distributive law. In fact, the correct answer, if no number is truncated, is 0.5555 E minus 1. Now let's move on the question 4. State true or false. First, minimize the number of arithmetic operations whenever possible. Avoid taking the difference of two nearly equal numbers whenever possible by alternate formulation of the problem. If it cannot be avoided, take the difference before doing other operations. Adding or subtraction numbers start with the smallest number and works with numbers in ascending order. Fourth is, do not formulate an algorithm that tests whether a floating point number equals 0. Fifth, third conditioning of problem is normally due to improper formulation and can be eliminated by carefully reformulating the problem. A practical way, if detect suspected ill conditioning, is to alter the two parameters by small amount and observe their effect on the solution. Sixth is, after a numerical algorithm is obtained, check if it can lead to numerical instability. In such algorithms, error grow in each step of the calculation. In such cases, reformulate the solution procedure to get a stable numerical algorithm. Seventh, if server rounding errors and consequent loss of significant digits are anticipated and no alternate formulation to avoid this is possible, then carry more significant digits in the critical calculation using floating point numbers in double precision mode. In this mode, the length of the mantis is twice that of the other floating point quantities. Eighth is, double precision requires large memory space and slows down calculation. Ninth, in the third iteration of finding the square root of 5 with starting point 7 using the Newton-Raphson method, relative error is 0.0013, and tenth is, the iterative method are compared on the following parameters. A. The rate of convergence. B. The amount of computational effort per iteration. And C. The sensitivity of the methods to starting value and the intermediate values. First statement is true. There are several reasons why it is beneficial to minimize the number of arithmetic operations whenever possible. First, efficiency. Performing arithmetic operation is a computationally expensive process. By minimizing the number of operators required, we can improve the efficiency and reduce the processing time. Accuracy. Each arithmetic operation introduces a certain degree of error which can accumulate over multiple operations. By minimizing the number of operations, we can reduce the overall error and improve the accuracy of the result. Uh, Robustness. Arithmetic operation can also lead to numerical instability and divergence, especially when dealing with large or small values. By minimizing the number of operators, we can reduce risk of numerical instability and make the algorithm more robust. Memory usage. Each arithmetic operation requires storage space in memory. By minimizing the number of operations, we can reduce the memory usage and optimize the use of available resource. Overall, minimizing the number of arithmetic operations can lead to more efficient, accurate, and robust algorithm with lower memory. The second statement is also true. Taking the difference of two nearly equal numbers can lead to loss of accuracy and numerical instability, especially when dealing with floating point arithmetic. This is because the difference between two nearly equal numbers can result in a very small number that may be lost due to the limited precision of floating point arithmetic. The third statement is also true. When adding or separating numbers with different magnitudes, it is important to start with the smallest number. To reduce the impact of the limited precision of floating point arithmetic, this is because small numbers have fewer digits and are less sensitive to rounding errors than the large numbers. It means Adding or separating numbers, starting with the smallest number and working with numbers in ascending order can help to improve the accuracy and numerical stability of the calculations, especially when dealing with floating point arithmetic. Here, statement 4 is also true. Do does not formulate an algorithm that tests whether a floating point number is equal to 0. It is not recommended to formulate an algorithm that tests whether a floating point number is equal to 0 because floating point numbers are not exact and their values may be subject to rounding errors. Due to the limited precision of floating point arithmetic, it is difficult to represent certain numbers exactly, including 0. This means that even if two floating point numbers are mathematically equal to 0, their representation in memory may differ due to rounding errors. Instead of testing whether a floating point number is equal to 0, it is better to use a threshold or tolerance value to check whether the absolute value of the number is sufficiently small. This approach is known as an epsilon test. Here is an example of an epsilon test algorithm in pseudocode. Function is 0 x epsilon, return ABS of x is greater than epsilon. In this algorithm, x is the floating point numbers being tested and epsilon is the tolerance value. The ABS function is used to get the absolute value of x and the function returns true if the absolute value is less than epsilon, indicating that x is effectively 0. Using an epsilon test, we can handle floating point numbers more accurately and robustly than testing for exact equality of 0. Fifth statement is partially true. Ill conditioning of problem can be due to improper formulation, but it can also be due to the nature of the problem itself. Ill conditioning means that small changes in the input or parameters of the problem can lead to the large changes in the output or solution. This makes the problem difficult to solve accurately and can lead to numerical instability. One way to detect suspected ill conditioning is indeed to alter the parameter by small amounts and observe their effect on the solution. However, simply altering the parameters by small amounts may not always be enough to eliminate ill conditioning. In some cases, a careful reformulation of the problem may be necessary to improve its conditioning. Therefore, by detecting suspected ill conditioning through sensitivity analysis is a useful first step. Addressing ill conditioning may require a more thorough analysis and reformulation of the problem. Statement number 6 is partially true. Numerical algorithms can indeed lead to numerical instability. Where errors grow in each step of calculation, this can be due to a variety of factors, such as ill-conditioned problem, numerical round of errors, or instability in the algorithm itself. To ensure numerical stability, it is important to carefully analyze the algorithm and its implementation to identify potential sources of instability. This may involve testing the algorithm on a range of input values, examining the behavior of the algorithm as the input values are varied, and comparing the results with analytical or exact solution where possible. If numerical instability is detected, then the solution procedure may need to be reformulated to get a stable numerical algorithm. This may involve using alternative numerical methods or algorithms that are known to be more stable, modifying the existing algorithm to reduce the impact of numerical errors or round off, or introducing additional constraints or assumptions to improve the conditioning of the problem. Therefore, while checking for numerical instability is an important step in the development of numerical algorithms, addressing instability may require a more thorough analysis and reformulation of the algorithm to ensure that it is stable and reliable for a range of input values and conditions. The statement number 7 is also true. Severe rounding errors and consequent loss of significant digits can occur in numerical calculation, particularly when dealing with quantities that vary widely in magnitude or when performing operations on values that are close to the limit of machine precision. In such cases, if no alternate formulation is possible to avoid this loss of precision, carrying more significant digits in critical calculation can help to minimize the impact of rounding errors. One way to achieve this by using floating point numbers in double precision mode, which allows for twice the numbers of digits in the mantissa compared to standard floating point numbers. This can help to increase the precision of critical calculation and reduce the potential for rounding errors to affect the accuracy of the final result. However, it is important To note that increasing the precision of calculation can also increase the computational cost and memory requirement of the algorithm. This statement is partially true. Double precision requires more memory space than standard single precision, as each double precision floating point numbers requires 64 bits, which is of 8 bytes of memory compared to 32 bits, which is 4 bytes, for a single precision number. However, whether or not double precision slows down calculations depend on the specific context and computational requirement of the algorithm. In some cases, double precision may be necessary to achieve the desired level of accuracy or to avoid numerical instability caused by rounding errors. In these situations, the benefits of increased precision may outweigh the additional memory requirements and computational cost. In other cases, where lower precision is sufficient or where the computational resources available are limited, it may be more efficient to use single precision floating point numbers or to consider alternative methods or formulations that reduce the impact of rounding errors on the final result. Ultimately, the choice of precision for normal algorithms should be based on careful consideration of the trade-offs between accuracy, computational efficiency, and memory requirements, taking into account the specific context and goals of the problem being solved. The statement doesn't provide enough information to determine its truth value. However, the method starts with an initial guess and iteratively refines it until a satisfactory approximation is obtained. The relative error measures the accuracy of the approximation by comparing it to the exact value. It is calculated as the absolute difference between approximation and the exact value divided by relative error of 0.0013 indicates that the approximation is close to the true value, with an error of only 0.13%. Therefore, the third approximation of the square root of 5 using the Newton-Raphson method with a starting point of 7 and a relatively error of 0.0013 is approximately 2.2411 when we take a guess. So when we make a guess, a relative error of 0.0013 is approximately 2.24119. And the last statement, 10th statement is correct. The iterative methods are commonly compared based on the following parameters. A rate of convergence, it refers to how quickly the iterative method converges to the desired solution. The faster the rate of convergence, the better the method. B. Amount of computational effort per iteration, it refers to the amount of computation required to obtain the next approximation in the iterative process. A method that requires less computational effort for iteration is preferred. See sensitivity of the method to the starting value and the intermediate values. This refers to how sensitive the method is to the initial guess and intermediate values used in the iterative process. A method that is less sensitive to the initial guess and intermediate. So that's it for the video. Thank you for watching. In next video we're gonna discuss second internal part A. So stay tuned with us. If you like this video, make sure you get a thumbs up. Thank you for watching.